This call is now being recorded.
Okay, so we will start a short new topic which is called geothermobarometry. Okay, so let's see what it actually means and what we can do with it. Okay, so the first question is, what is geothermobarometry? Okay, so if you look at this word, then there are a few parts of it. One is geo, one is basically thermometry, one is barometry. Okay, so what do we mean by thermometry? Can somebody say, or barometry? Do you have an idea?
So thermometer means temperature and barometer is the pressure.
Right. So thermometry is finding out the temperature, okay, or estimating temperatures. Barometry is estimating pressures. Then there is a word which is geo, which is basically in geological conditions. Okay. So that is termed completely clubbed together in a term which is called geothermobarometry. So of geological situations or geological conditions, estimating temperatures and pressures. Okay. So geothermobarometry is the method of estimating the temperature and or pressure of the formation of igneous and metamorphic rocks. Okay, so that is what geothermobarometry means. Most commonly used for metamorphic rocks. It's more commonly used for metamorphic rocks rather than for igneous rocks, right? And this is what geothermobarometry means. Now, how we can estimate the pressures and the temperatures? The first one obviously is a qualitative way. Qualitative way, if you tell me that we have discussed these qualitative ways, for example, we discussed the such a stability field or a stability field of the quartz or the stability field of aluminosilicate. Okay, so from the stability field of a particular mineral, we can have an idea about the pressure and the temperature condition, but it is not that precise. Okay, if you say sillimanite, let's say the stability field of sillimanite or rock content sillimanite, we know the stability field in which or the conditions in which it is formed, but that's a pretty wide range of conditions in which sillimanite may form. Kyanite gives an idea, obviously, that it is relatively higher pressures. Andalusite gives an idea that it is a relatively lower pressures, but this is a more qualitative way. For example, if you talk about the variance or the pseudomorphs of quartz, you can also give an idea. For example, when I say coesite, obviously we know that these are much higher pressure forms of quartz, which means that formed at a very high pressure. And you can see that the range of PT conditions in which coesite can form is pretty wide. So just by saying the stability of coesite, we cannot determine the exact PT condition. Okay, so these are qualitative ways. Okay, one more qualitative way is obviously the PT, the facies diagram, okay, which we have discussed about, which depends upon obviously the bulk rock composition, as well as depending on some of the index minerals or a mineral assemblage, we can determine, okay, let's say it is in the amphibolite facies condition or in the granulite facies condition. So when we can determine a rock in the amphibolite facies condition, what we can say is a range of pressure and temperature, but we are not exactly sure that in which range or which region of the amphibolite particular facies does this rock was metamorphosed or formed. Okay, so this is a little bit more precise than from a particular mineral, but but it is also a qualitative way of determining the pressures and the temperature conditions of metamorphism or the formation of the rock. Okay, but what we are what we will see today is a quantitative way, mathematically, how we can determine the pressure and the temperature conditions of formation and what is the principle used behind that mathematical calculation. Okay, this is what is in this short part of geothermobarometry, right? Okay, so quantitative geothermobarometry, this is what we are going to do in this section, right? So what is quantitative geothermobarometry? Calculation of equilibrium temperatures and pressures from the measured distribution of elements between coexisting phases. So what we are trying to do is calculating the equilibrium temperatures and pressures, which means that, for example, the different mineral assemblages, the temperature and pressure in which they were in equilibrium with each other from the measured distribution of elements between the coexisting phases. Let's say mineral A and mineral B coexist with each other. Okay, and we can see from the texture of the rock that A and B formed together or coexisted together in equilibrium. Okay, coexisted together in equilibrium. Then from the distribution of elements between these two coexisting phases, A and B, we can calculate the pressure and the temperature conditions of metamorphism. Obviously, if the distribution of these elements are dependent on pressure and temperature. So that is what we will see. So if the distribution of those elements between these coexisting phases are sensitive to temperatures and pressures, so from these measured distributions of these coexisting phases, we can find the pressures and the temperatures in which it got metamorphosed. Mainly what we mean by the formation of metamorphic rocks. Okay, so we are aware of the compositions of virtually every solid solution phase in a rock, whether it is metamorphic or igneous in origin, and this composition, solid solution compositions, okay, or varies with temperature and pressure because of the exchange or continuous reactions. Okay, so these compositions are many a times dependent on the temperature and pressure. For example, if you think of the simple example of the anorthite content of plagioclase, okay, this is a solid solution mineral. We have seen that the temperature at which the anorthite from a particular melt, the temperature at which a particular solid solution would form is dependent on the temperature, even if we are fixing the pressure. Okay, this is true for many other minerals or most of the minerals which show solid solution, where the composition, okay, of the solid solution phase is related or can be related to the temperature and pressure. Now the point is, if we can determine this relation mathematically, then we can use this relation and the compositions what we can measure to uh, to calculate the pressure and the temperature of formation. Okay, that's the basic principle behind quantitative geothermobarometry. Okay, so the compositions of the minerals involved in many of these reactions can be sensitive indicators of pressure and temperature conditions. Okay, these are sensitive indicators of pressure and temperature conditions. If we can mathematically relate the change in temperature and pressure with the changes in the mineral composition. So that's the important part. If we can mathematically relate the change of temperature and pressure with the change of mineral composition, we can determine the temperature and pressure by measuring the composition of naturally coexisting minerals. Okay, that's the principle. Our idea or aim is to mathematically relate the change of pressure and temperature with the changes in mineral composition. And how we can do that? Basically, it has to be done by experimental part, which is called experimental petrology, which means you need to run experiments, okay, similar to experiments what is run in a chemical lab. The same experiments, of course, you have to raise the temperature and pressure, which is equivalent to geological conditions. Okay, you have to do experiments in high pressure and temperature conditions between different minerals or mineral pairs and establish the relation that how temperature and pressure uh, is related to the changing compositions of the minerals. So if we can get a basic data or this relation from the experimental petrology, when the relation is established, then we just need to measure the compositions of the naturally coexisting minerals. And if we can measure successfully the compositions, which is done very easily, we can find out the temperature and pressure in which these mineral pairs were in equilibrium with each other. Okay, And in a rock, when we see some mineral pairs coexisting with each other, which means that is the time when the rock formed, and ultimately what we get is the pressure temperature conditions on the formation of that rock. Okay, so that's the background for quantitative geothermobarometry. Okay, any questions from here?
Sir, in last line, like by the like mineral composition, we can like correlate the temperature or pressure. Like you mean,
Sorry?
like in this last line,
Hmm.
like the mineral composition. By the mineral composition, like we can like correlate the temperature or pressure. You mean that?
See, if we can find the relation that if the pressure and the temperature changes, how the composition of the mineral pairs or the mineral changes. If we can find the relation, let's say mineral A and B. Okay, mineral A and B is coexisting at 100 degrees centigrade, just for, or let's say 500 degrees centigrade, just for a sake of saying. Okay, mineral A and B coexisting with 500 degrees centigrade. Okay, mineral A and B has a particular composition. Okay, now if you increase the temperature to 600 degrees centigrade, then the composition of both A and B changes. Okay, we have seen with metamorphic petrology the changes in the composition of the mineral. Now the composition of both A and B changes by different reactions or exchange. We will see what are the relations. Now, if these change in composition of A and B can be mathematically related, if we can find a mathematical relation between the change of the temperature and the pressure, let's say from 500 to 600, and the change in composition of A and B, if we can find the mathematical relation from doing experiments in a control system, then we can use that relation for any compositions of the naturally occurring mineral A and B and find out the temperature and pressure in which it has formed. That's the basic background.
Okay, sir.
Okay. Anybody else has a problem with this basic premise of geothermobarometry?
No, sir.
Okay, let's move on. Okay, so before getting into the detail of how we do it, it's very important to understand or be aware that why we do it. Okay, why do we need to know the pressure and the temperature condition of metamorphism? How does it help us, right? On a broader, for the sake of learning, or there are broader aspects or broader reasons as well. Okay. So metamorphic rocks of different ages. Why do we do it? Metamorphic rocks of different ages record the conditions of the deep crust throughout the geological history. Okay. As we know that the metamorphic rocks or the process of metamorphism has been operating throughout the geological time. Okay. So these metamorphic rocks of different ages, means at ages where they are formed, record the conditions of the deep crust. As we said, this metamorphism is strictly related or dominantly related to the crustal part. So we call it as a metamorphic rock when it has a crustal signature. Okay, so basically from mid to deep crust, it records all the conditions throughout the geological history. Okay, if you basically pick a rock which is, let's say, 500 million years old, okay, you can find out, so that rock has recorded the conditions of the deep crust at the depth where it has formed at of that time. Means these are the only means of finding out, or which preserves the record of the situation at that age. Okay, at that geological age, we did not have any other source of finding out what the conditions are. So the rocks are the only which have stayed from that time. These old rocks are the only possible ways of finding these conditions. And if we can decipher the pressure and the temperature conditions recorded by these metamorphic rocks, we can, obviously some word is missing out here, we can unravel the conditions in the deep crust and the processes operating out there, which is not possible to retrieve by any other means. You cannot tell me, or you cannot possibly find any other means of finding out the pressure and the temperature conditions of the deep crust, let's say 500 million years ago. Okay, it is only the rocks which have preserved this information which are of that age. Now our task as the petrologist, metamorphic petrologist, is to retrieve that information from that rock. Okay, and geothermobarometry is the way of retrieving the pressure and the temperature conditions. Okay, for example, geochronology is the process by retrieving the age of the rock. Okay, along with the PT conditions, we can determine the time of metamorphism. Obviously, that is the age and what we call as geochronology. We will be able to track the thermal evolution of the crust through time. Okay, we will be able to track the thermal evolution of the crust through time. So the thermal history of the Earth is poorly constrained. The only way to make it better is extensive study of metamorphic rocks of different ages. Okay, you can see some recent very good review papers which says that the contribution of metamorphic petrology to understanding the lithosphere evolution and geodynamics. And an extract of this paper says that the robust quantification of the pressure, temperature, and time that followed these advances has provided reliable data to benchmark geodynamic models and investigate the secular change in the thermal state of the lithosphere as registered by metamorphism through time. Okay, so basically the robust quantification of the pressure, temperature, and time has given us a very good understanding of the change or the secular change of the thermal state of the lithosphere, which is actually the lithospheric evolution and geodynamics. But still lots to be done. Okay, lot more to understand, and still the thermal history of the Earth is poorly constrained, and the only way to make it better is extensive study of metamorphic rocks. And the metamorphic rocks are the only possible ways or possible what means that we have to find out the conditions operating or conditions of the crust, okay, from throughout the geological time. There is no other means. Right. Any questions on that? Any questions?
No, sir.
Pankaj? Pankaj? Any questions?
No, sir. No, sir. It's fine.
Okay. Nitya, any question?
No, sir.
Okay, good.
Sir, uh, but sir, through seismology, we can determine uh, the rock conditions, like in which form the rock is there.
Absolutely, absolutely, but that is the present day condition. If you talk about the present day conditions, that's the only means. Obviously, we can't get deep into the earth, but you are not sure. You have seen we have enough record that the earth is a dynamic planet, right? So what was the situation or what was the condition 500 million years ago is not the condition same as now. It has changed dramatically. So seismology obviously gives the rocks or what is happening or the structure of the rocks or the structure beneath the surface, but this is the present day condition. Okay, seismology or practically no life was there before that. So no humans were, means there's nothing. So there's no other. We can't do seismology of the rock and find out the condition, and which is way back in geological history.
Yes,
Okay.
sir. Yeah.
So that is the difference. Right?
Okay, sir.
Okay. So have you heard of this term, Gibbs free energy?
Yes, sir.
So where have
Yes.
you done it? In
In
any
thermodynamics.
geology course or thermodynamic course, or means related to earth, in earth science course, or somewhere else?
In
Sir,
chemistry course.
In chemistry course.
Sir, in mineralogy course as well, we studied a bit.
Studied a bit. Okay. So basically, we will now Gibbs free energy is is the term which is used very extensively in chemistry, or in everywhere. In fact, physics, chemistry, quite a lot. And for these things, for geothermobarometry, the principles of chemistry are all applicable. Okay, because these are all chemical reactions, and the principles of chemistry are most widely applied in this. Okay, many of things what I show is basic chemistry, but the principles of geothermobarometry also lies on that. So what I'll try to do, give you the aspect of geology to these simple things on the simple chemistry that we already know. Okay. So if you define it, obviously Gibbs free energy is the energy that can be freely converted to work. And mathematically, we know we can write it as G equals H minus Ts, where H is what is H?
So enthalpy.
Enthalpy. H is enthalpy. S is
Entropy.
S is entropy. Okay. So the Gibbs free energy varies as a function of pressure, temperature, and the composition as well. Okay. There is a simple of a particular phase. It is written, but we can it varies with in geological system. It varies with pressure, temperature, and composition, and obviously the equation modifies depending on these functions: pressure, temperature, and composition. Okay. So Gibbs free energy is used to assess the stability of chemical system. I think this is also what you have done or know from chemistry. Stable forms of chemical systems are those with a minimum possible Gibbs free energy for the given condition, right? And you know probably this as well. Okay. For example, let's say why would kyanite be present in this condition, sillimanite here and andalusite here? Because under these conditions, the Gibbs free energy of kyanite is less than that of the other two polymorphs, which is sillimanite and andalusite. And therefore, the kyanite is stable. Under these conditions, sillimanite, the Gibbs free energy of sillimanite is less than that of the other two, and therefore sillimanite is stable. Okay, Gibbs free energy is the minimum Gibbs free energy, or stable forms of chemical systems are those with the minimum possible Gibbs free energy for a given condition. That is very important for a particular condition. Similar to that of the different polymorphs of quartz as well. So what we basically see is the minimum Gibbs free energy, which makes it stable. Okay, if you can calculate, there are mathematical ways of calculating it. We will try to do this in a practical as well. That if you calculate the, let's say, the Gibbs free energy of kyanite, sillimanite, and andalusite at different conditions, you will see that the stability field in which both are sillimanite is stable, it will always be that the sillimanite will have the lowest Gibbs free energy. We all know this. Okay, now Gibbs free energy also gives of a reaction is used to assess the direction of a reversible reaction. This is also your knowledge from chemistry. For example, if we have a hypothetical reaction like this, where A in different coefficients or different proportions, A and B react to form C and D, then the Gibbs free energy of the reaction, okay, the difference between the Gibbs free energy del G is basically the Gibbs free energy of the products minus the Gibbs free energy of the reactants. Okay, so now Gibbs free energy of C plus 4 into Gibbs free energy of D minus the sum of the Gibbs free energy of the reactants, that gives you the difference in the Gibbs free energy del G. Now the del G will determine that which direction the reaction will move at a particular condition. Okay, the side of the reaction with lower del G will be more stable, obviously. So if on the right hand side of the reaction has a lower del G, then the reaction will move from left to right. If the left hand side of the reaction have a lower del G value, then lower G value, it's not the del G, the lower G value, which means that the reaction will move from the right hand side to the left hand side. And we all know that, right? Is it all fine?
Yes.
Yes,
Okay, so we call it as a forward or the backward reaction, right? And the unit for G is obviously the Gibbs free energy is always joule. Okay, for example, if you take any reaction, let's say the reaction on the left or the reaction on the right, so this will depend on the Gibbs free energy. Okay, or in other terms, the del G. If del G equals 0, then we are in the equilibrium condition. If del G is negative, which means product minus the reactant is negative, which means that the del G of the products is less than that of the reactants, we have a forward reaction, which means moving from left to right. If the del G of the del G is positive, which means a backward reaction, which means that the del G of the left hand side is less than that of the right hand side. Okay, so this also determines the direction of the reversible reaction, and we all know this. Okay, now let us come to a little bit that is same as that of the chemistry. Now it is a little bit modification from what you have done in chemistry, that if we are dealing with solid solutions. Okay, we are dealing with solid solutions, which means the temperature composition relationship. Now, if we are dealing with minerals, which shows solid solution, and there is a relationship between the temperature and the composition of the minerals, then we write the equation in a slightly different way, or the equations can be modified in a slightly different way. Okay, all these reactions obviously one can derive, but we do not have enough time of teaching igneous and metamorphic petrology together to come to the derivation of these reactions. So to give you the principle of geothermobarometry, we start with the reaction itself. Okay, for example, if we have the same reaction, 2A plus 3B equals C plus 4D, and A, B, C, D are different minerals, which shows a solid solution. Okay, for example, A is orthopyroxene or whatever. B, C, D, these different minerals show a solid solution. Then basically in which the composition of one or more phases is variable, which means that these minerals show solid solution. We can solve the equilibrium curve using the equation at a constant pressure and temperature. Okay, then basically what you have to do, you have to stabilize at a constant pressure and temperature. We can use this reaction. Okay, where del G at a particular pressure and temperature, right? Del G at a particular pressure and temperature, which is the constant pressure and temperature, equals del G0 plus RTL and K. Okay. Now at a particular, we know that at a particular pressure and temperature, if the minerals are in equilibrium, which means that A plus B equals A plus 3B equals 4C plus 4D, means A, B, C, D are in equilibrium with each other, then del G equals 0. Okay. Now if del G, this part becomes 0, then we can rewrite this equation at equilibrium. Okay, so this is the equation at equilibrium, where we will see where del G 0 PT, we will come to it what it is. RT, the different values will come, where K is the equilibrium constant and it is defined by this equation. Okay.
Sir, can you please repeat once again? Why del GPT is 0?
Del GPT is 0 because the reaction is in equilibrium. We just saw in the previous one, right? If the same reaction, if del G equals 0, which means that the G of the products is equal to the G of the reactants, which means AP 2A plus 3B equals C plus 4D. This is in equilibrium, which means A, B, C, D are in equilibrium with each other. Okay, so that is what we did.
Okay, sir.
When do we have 0? When the two reaction minus products are the same, the summation of the G of the reactants and the summation of the G of the products are same, which means they are in equilibrium. Okay, and that is when del G equals 0. Now we are trying to find out the equilibrium condition. Okay, so if we took a generalized reaction like this, the same reaction. Okay, now if these phases A, B, C, D, one of them or all of them have solid solution, okay, which means that the compositions of them are variable, right? If the compositions are variable, we write the reaction in this way. As I said, now the derivation of the reactions, we are not going into it, but this is the reaction, what we write. Okay, where del G at a particular pressure and temperature in which we are trying to find out, okay, equals del G 0 PT, this term we will define, plus RT ln K. Now this part, as the equilibrium, as they are in equilibrium at a particular pressure and temperature condition, this part becomes 0. Okay, yes. We are trying to find out the equilibrium condition, so basically this part becomes 0. Now if this part becomes 0, the equation can be rewritten like this. Now we are trying to define each of these terms, how it is done. Okay, so there is one term K, this is called the equilibrium constant, and we can write it in this format. Okay, so let's see the next slide. Okay, so what is A? This A is basically the activity. Okay, activity of the different phases. Okay, here obviously activity means activity of C, activity of D, activity of A, and activity of B. Okay, so these are the activity. Now what is activity? Activity is defined as the effective concentration of the substance. Have you done this activity in your chemistry? Have you done activity in chemistry?
Yes, no, sir. We have done something like that in environmental geoscience course in secondary.
Okay.
Sir, so instead of activity, we use molarity in the equations.
Mu, right?
Yes.
No.
Yes,
no,
sir,
not mu. That's what did you use?
Sir,
molarity, sir.
Sir, actually, not everyone took chemistry and so.
Okay. Okay. Anyways, so I'm keeping it simple so that everybody gets the principle of it. Okay. So it is defined as the effective concentration of a particular substance. Okay. So this is the activity of it. Means basically what I mean is that this activity is dependent on the composition, where activity chemically or mathematically is defined as X and gamma. Okay, X into gamma, whereas X is the mole fraction and gamma is the activity coefficient. Now, if the activity coefficient equals 1, okay, let's say if the activity coefficient is 1, then the activity is equal to the mole fraction, right? Mole fraction of a particular element in that substance. Okay, for example, we call it as xmg, right? Now, which is basically the mole fraction of mg in, let's say, orthopyroxene, in, let's say, garnet or anything else. So the activity becomes equal to that of the composition. So if we know the composition of the rock or composition of a particular mineral in question, we can know the activity. Okay, if we know the activity, we can calculate the K. Okay, if we know the activity of each of these different minerals, A, B, C, and D, we can calculate the K. Okay, let's see what are the other means. What is del G0 PT? Is that it is the Gibbs free energy of the reaction for a pure phase at a pressure and temperature of interest. There are two terms. One is the pure phase, okay, and one is the pressure and the temperature condition of interest. Okay, which means that what is pure phase? Pure phase means without solid solution, basically end member. Okay, so we know G equals H minus Ts. Okay, from here, if we, for each of the mineral, we can find out what is the G for a pure phase, means without solid solution. Let's say for OPX, enstatite. Okay, we can find out the G for enstatite. We can find out, let's say, grossular. Okay, each of these end members, we can find out what the G is, right? So we have and what is the pressure and the temperature of interest? Means the value at which we already know the value or the Gibbs free energy. Okay, so how it is done? Obviously, it is done through experiments. Let's say our condition, normally the condition what we have is 1 bar pressure and 25 degrees centigrade. If we know the value of a known condition, what that can be anything, we can find out the Gibbs free energy of the different end members. So if we know that, then we know this value as well. Okay, K we can find out from the composition. Okay, R is the universal gas constant, that is also we know the value. So if you now go back to this reaction, the unknown what is remains is only temperature. Okay, so this is just to give you an idea that the unknown remains only as the temperature at which this reaction of these reactants are in equilibrium with each other. So if we know all the other values or find out the other values, we can know the temperature as well. Okay, any confusion in this concept? Okay, any confusion in this concept?
No, sir.
So others, any confusion in this concept?
No, sir.
Sir,
Yeah.
sir, in the previous slide, why we use activity coefficient as 1?
No, we don't have to. We don't have to. Let's say, even if the activity coefficient we know, then basically it's a number. We don't have to use 1. I said that if it is 1, then it is activity is same as that of the mole fraction. Okay. In many cases, the activity coefficient may not be 1, but then we know the value. It's a numerical value. Okay. If it is a numerical value, whatever be the value, the activity is directly related to that of the composition, which means that if we know the composition, which can be directly measured in a particular mineral, we can know the activity.
Okay, sir.
Okay. Okay. So for many of our calculation purpose, we do take it as one, right? We do take it as one, but it doesn't matter. We don't have to get into that confusion. So whatever the activity coefficient is, it's a numerical value. And if it is a numerical value, then activity is directly proportional to the composition. Now the composition we can directly measure from the rock.
Okay, sir.
Okay, understood. So what I tried to mean from here is that this activity or this K value can be found from the activity. This is how we write. What is activity? Activity. Yeah, so how do we define, how do we write this activity? As you can see out here, K equals activity of the sum, or sorry, the product of the activities of the right hand side of the reactant, okay, C and D, raised to the power of the coefficient, divided by the product of the activities of the left hand side of the reaction, raised to the power of their coefficients. So activity of C into activity of D to the power 4 divided by the activity of A to the power 2 and activity into activity of B to the power 3. So this is how the K is defined, okay, for all reactions. Now for to find out the K, we need to know the activities. Now what I mean to say, this activity, this term is directly proportional to the compositions of the different compositions of the minerals which we measure. Okay, compositions of the minerals. So basically, this term K in this reaction can be found out from the compositions of the minerals. So this is the link between the pressure and the temperature conditions, and or the Gibbs free energy and the pressure and the temperature conditions and the compositions of the minerals. Okay. Okay, all fine.
Okay, sir.
Okay, so we come to another concept, okay, which is called the Clausius-Clapeyron equation, which also can be derived, okay, which also can be derived from the basic principles of thermodynamics. But as we are not getting into the details of thermodynamics due to the, first of all, due to the lack of time, and then again in this online mode, it's very difficult to give the concept. So I'm giving you only the resultant product and its application in geothermobarometry, which would be easier to understand. Okay. So for an equation or for a reaction in equilibrium, the del G equals 0. At that condition, we can write basically this equation. Okay, so basically derivative of del G equals del V into dP, okay, change in volume into small change in pressure minus the change in entropy into dt. Okay, now at equilibrium conditions, obviously del G equals 0, therefore this part becomes 0 and the equation reduced to this, and therefore we can write basically dP by dt equals del S by del V. Now in a PT space, okay, in a PT space, what does dP by dt means? What is dP by dt? It's a slope. Very good. So any slope of this, any slope of the line is given by dP by dt. right? So dp by dt gives the slope of the line. Okay. So now what we see is that from the relation that dp by dt, which means the slope, is directly related to del S by del V, which means the change in entropy. Del S is the change in entropy by change in pressure. Okay. For any reaction, let's say A plus, the same reaction we can consider, maybe. Let's say 2A plus 3B equals C plus 4D. For this reaction, okay, for this reaction, dP by dt, which means the slope of the reaction in PT space, will be determined the change in entropy divided by the change in, dP by del S by del V. I wrote P, sorry. Change in entropy divided by the change in volume, which means what is change in entropy is the summation of the entropy of C, okay, plus entropy of D, okay, 4 into entropy of D, that is the entropy of minus 2 into entropy of A minus 3 into entropy of B. So this will give you del S, and similarly del V. Okay, del S, and these are the volume. Okay, so the slope of this reaction in the PT space would be determined by the change in entropy by change in volume, which means that when do we have a higher slope? Okay, a steep slope or a higher slope?
When there is higher entropy and less volume change.
Okay, so when the change in volume is very low and the change of entropy is very high, we will get a steeper slope. And when do we get a shallower slope? When do we get a shallow slope?
When the change in volume is high and change in
Right, when the change in volume is high. So any reaction where the change of entropy is very high with very less change in volume will have a steeper slope. On the other hand, any reaction where the change in volume is very high and very less entropy change will have a shallower slope. Now in a PT space, if we have a reaction like this, let's say A plus B, C plus D. Okay, same as this one. Let's say 2A plus 3B, C plus 4D. Okay, this is this reaction where the slope is very steep. Okay, so if the slope is very steep, so it is sensitive to temperature or sensitive to pressure. What can we measure from a reaction which has such a steep slope? Means what can we measure, leave it. So is it more sensitive to temperature or pressure? Okay, which means that the reactions will occur. Let's say 2A plus 3B combines to form C plus D. Sorry?
Sensitive to temperature, sir.
Okay, others do agree, or do you have a other point of view?
Yes, sir, sensitive to temperature.
Okay. So what do we actually mean by sensitive to temperature? Means that if we change a little bit of temperature along this boundary, along this region, we will have either 2A plus 3B or C plus D, which means that if we have C plus D, you can say, okay, we are above this temperature range. If we have A plus B, then you are below this temperature. So it is very sharp to temperature. It is more sensitive to temperature. But it is not pressure sensitive to pressure, because you can be all throughout this pressure, you can have only one assemblage, let's say A plus B or C plus D, with a range of pressure. Means if you change the pressure a lot, even if you change the pressure a lot, the mineral assemblage won't change much. But if you change the temperature a little bit, the mineral assemblage would change, which means that this is more sensitive to temperature. On the other hand, if we have a reaction with a shallow slope, okay, E plus F, let's say G plus H, is it temperature to pressure or is it sensitive to temperature or pressure?
Sensitive to pressure.
Sensitive to pressure. So we will be able to measure the pressure much more from this, which means if we change the pressure a bit, we are going from one phase to the other, one assemblage to the other, which means we can know that whether we are lower to a particular pressure or above particular pressure just from the mineral assemblage, which means it is sensitive to pressure. Now, the reactions which are sensitive to pressure are good barometers. We can measure the pressure conditions better from these. On the other hand, the ones which are sensitive to temperature, which means have a steeper slope, are good thermometers. Okay. Now this reaction out here, sorry. So this reaction out here, which has a steep slope, what should be dP by dt? Is high, right? dP by dt is high?
Yes, sir.
Yes, sir.
So del S by del V? Sorry. I mean del V, okay. Del S by del V equals?
High.
High, which means you have very low volume and large entropy change, right?
Yes, sir.
So any reactions where the entropy change is very high and the volume change is very low, this would have a steeper slope and therefore would act as a good thermometer. On the other hand, if dP by dt is low, del S by del V will also be low, which means that very high volume change and low entropy change. If a reaction has a very low entropy change and very high volume change, which means it will be low, and that will act as good barometers. Okay, is that correct or is that understood?
Yes, sir.
Okay. Okay, so let's keep it till here. So if you have any questions, you can ask me. We will start from this tomorrow. Okay, so tomorrow I'll try to take the class from 9. Be ready for that. If I have to come to the institute, then I won't be able to take from 9, then I'll take from 10. This I'll let you know by tonight. Okay, but be ready. Most likely it will be from 9 to 11, 2 hours. Okay.
Yes, sir.
Okay, sir.